Okay, so implicit differentiation, this is the last new section before our test review. So, but even when we're in test review, starting tomorrow, there's still kind of few things we need to kind of clean up in terms of especially some of the graphing problems we haven't quite seen yet. So we'll definitely spend some time finishing out the rest of the packet, and I'll also give you a test review packet. If not tomorrow, I'll give it to you Wednesday. So we'll have a couple of days to review for our test. Now our test is really only 2.2 to 2.5. I'm not going to include limit definition on it. So just 2.2 to 2.5. Okay. So the last new topic is implicit differentiation. So let's talk about what that means. Everything that we've seen so far in terms of equations have been these explicit equations. We call them explicit because they are solved for y, explicitly solved for y. So everything that we've been working so far have been nice, clean functions in the sense that your y's and x's are never kind of mixed within each other. You never see anything done to the y. There's no like square root of y or y squared or multiple y terms. It's always just y equals and x's are separated, and the left side is nice and clean. It's just y equals. So these are equations where x and y's are separated on different sides of the equation, and the y is cleanly by itself. It's just y equals. And these are going to be functions because they are always going to pass a vertical line test. We never are going to have these graphs that overlap each other. So, and we know how to find the derivatives for these. A lot of times we've done power rule, product, quotient, chain. They're all nice, clean functions for us to apply. Now, implicit equations, these are ones where it's not explicitly solved for y. And visually, what that looks like are equations where x's and y's are mixed together on the same side of the equation. Now, they may not necessarily be mixed together. It's just you see something strange about the y variable, either multiple y terms or y squared or square root of y. Anytime we see something strange done to the y variable, that's an indication that we have to go through an additional step if we want to find the derivative, a slope formula. But we can still find a slope formula for equations that are not necessarily functions. Okay, it's just that we have to do a little bit more steps to get there. So to kind of show you that distinction between the two of them, let's go through and find the derivative like we normally would with an explicit equation, and we know how to do that. So let's just go through this process here. So y, what do we call this? Y's derivative, we would call this what? Y prime, right? Or dy dx. Right? And then every term, we just go through a derivative process. 3x squared becomes, 6x minus 27x squared, and then plus the 5 goes away to 0. Now, we found the derivative. We know how to do that. Now, let me talk a little bit about some behind the scenes things that we've been kind of leaving out because we really didn't need all that behind the scenes stuff. But now it's going to be more helpful to kind of see it so that we can kind of distinguish some things that we have to now deal with. So technically, we are doing something on the left side, but we just call this dy dx, right? We never thought of it as, oh, I'm taking a derivative of y. But that's basically what we're doing. We're finding the derivative of y, and the derivative of y is 1, and we are still finding the derivative of this dependent variable. So anything that is a dependent variable, we have to represent a notation to indicate that I'm finding the derivative of this dependent variable with respect to my independent variable x. So all that behind the scenes stuff we just left out and just said, oh, that's just my derivative notation, and so y becomes dy dx. Okay, but I'm going to kind of show you this with the purpose in the sense that this is going to connect with something or equations that are not functions. Okay, we said 3x squared was just 6x, which is great, but technically we're finding the derivative of x with respect to itself. So technically there's a dx over dx going on behind the scenes. And then the 9x cubed becomes 27x squared, which we did do. And then technically we're attaching dx over dx. Now, every variable kind of has this thing going on, but we ignore the dx over dx because any variable by itself is just one. So we never really did anything special with the x's. But basically, because the y is a dependent variable, that dy dx is not going to quite go away. So it's going to have to stay, and it's going to represent the derivative variable. Okay. Now, all this is to say that when we are coming across y's in the future with these equations where y's are not quite by itself, that's how we keep track of these derivative variables. So here is what we're going to do. We're going to take the derivative of each term like we normally would with respect to x, right? But if a variable is y, we're going to find its derivative, but we got to do something extra. We're going to find its derivative, and we're going to immediately attach a dy dx because we have to keep track of these dependent variables. Okay, so let's do that process, and I'll talk about the rest of the steps. Okay, y squared minus 5x equals 4. These are all nice, clean, power rule terms. There's nothing that's messy about these variables. We just have to go through this process. Okay, but first we recognize that okay, there's something a little bit different about this equation, right? The y is not by itself. There's something done to the y variable. So anytime there's something different done to the y variable, you have to go through this implicit differentiation process. Okay, so let's go through and find the derivative. Okay, what does y squared become? 2y, right? So you find the derivative like you normally would. But as soon as you take y's derivative, you need to include and keep track of the fact that it's a dependent variable and there's a derivative notation that's going to come out of that y variable. Okay. All right, next up, 5x. So we treat it like we normally would. Don't do anything different. 5x becomes just 5 and nothing more. Okay. And then the 4, treat it like we normally would. 4 goes to what? 0. Good. So now we're dealing with an equation. So just keep in mind that if you see a constant by itself, it's not immune to the derivative process. It is also being impacted. Every term that we see, we have to put it through the derivative process. We can't let that stay a 4. It's going to have to go to a 0. Okay. So the calculus portion is done. Now the rest of it is just trying to get that dy dx by itself. So we're going to try to isolate the dy dx term by itself on one side of the equation. And then we're going to move all the other terms to the other side of the equation. And then we're going to factor out the dy dx and then divide it over. So basically, just algebraically, we're just trying to get that new variable by itself. Okay. So look at how this is set up here. What can we move first? Yeah, let's just move that 5 over. Almost there. This is one of the easier problems to begin with. What's the one more step to get that dy dx by itself? Yeah, divide by 2y. So this is the slope formula for whatever this equation looks like. Okay. So as I said before, our calculus derivative process will get messier because we're dealing with more and more complex equations. But I don't want us to lose the big picture. The big picture is we're starting with a curve and we end up with a formula that describes the curve's behavior in terms of slope, right? So if I give it some location, in return, it'll give me a number, and that number was going to correspond with how steep that point is on the graph. So let's not lose the big picture here. It's still doing the same things as other derivatives. It just looks a little bit different. And what's something that stands out about this derivative that we haven't seen before?
There's a y.
There's a y, yeah. So it requires a bit more information. Your equation is not quite a function. So with the fact that you may have curves that overlap each other, it needs more information in terms of where that point is. So sometimes it needs both an x and a y. Sometimes it only needs a y, but it's going to have to need more information, especially if the graph is not as clean as a function. So yeah, it still does the same things as other derivatives. It just looks a little bit different because the graphs are looking more complicated. Okay, any questions with that process? Okay, so the first thing that we really need to do is to look at an equation and understand, okay, that's not a function and I need to go through implicit. So basically, if your y variable looks out of place, or if your y variable looks like it's something done to it, or you have multiple y variables, that's an indication, oh, I got to go through this additional process. I got to go through this implicit differentiation because my y variable is not clean and isolated like other functions. Okay, so let's go down to example 1. Okay, x squared minus 2y cubed plus 4y equals 2. We want to find the derivative equation. First, do we recognize the need for implicit? Yes, right. We see a couple of y's. We see y cubed. We don't see y equals. So we immediately need to recognize, okay, there's something different about this equation. The y's are out of place. I need to involve implicit. But the nice thing here is everything is power rule. Everything is pretty straightforward. We just have to keep track of our additional variables. Okay, one term at a time. X squared becomes x. There's nothing new and different with x's. We treat it like the same thing and we don't do anything different. Okay, minus 2y cubed becomes 6y squared. We just took y's derivative. What else do we need? We need to attach and dy dx. Yeah. Okay, good so far. All right, next up, 4y. What does 4y become? 4. Anything else? Dy dx. Because we are asking for y's derivative, we need to attach a dy dx. Now, this is where I see some students run into some trouble here. They see the y disappear and they figure, well, there's no more y, so I don't need to worry about dy dx. So even if the y disappears, we need the dy dx because we're asking for y's derivative. So we need that dy dx there, even if the y disappears. Okay, and then equals 2 is also impacted, so 2 goes to 0, right? So that's another common mistake that I see. I think it's just easy to feel like, oh, that's just a 2, so I'm going to keep a 2 there. But I think because that 2 is by itself, we think, oh, we just take the derivative of one side of the equation and leave the other side alone. But every term on both sides is impacted. Okay, okay, so now we're done with the calculus. So now we're just trying to get that dy dx by itself. But first, we're going to isolate the dy dx. Okay. Let's leave the dy dx terms on the left side, on the same side, and then we're just going to move the non-dy dx terms on the other side, because eventually we do want to factor that dy dx out. So I'm going to move that 2x over. Okay. Any questions with that steps there, right? So we're done with the calculus. Now we're just rearranging and algebraically trying to get that variable that we want, that dy dx variable by itself. Okay, so now we can cleanly factor out the dy dx. Now there may be other common factors, but you only care about isolating dy dx. So let's ignore the fact that we could probably factor out more than just dy dx, and we just focus on the dy dx. So if I factor dy dx, whatever is left, I'm going to leave inside the parentheses. Okay, final step. Divide by the parentheses, right? Or whatever's inside of it. So you see that this derivative looks a little bit more complicated because normally we don't expect derivatives to kind of have all those variables. But now, because the equation looks a little bit different, it needs more information. But it still does the same job as before. It just tells us about the slope behavior of the original equation. Now, let me just kind of give a quick example as to why an equation, a derivative, may need more than x and more than just the x value. Let's say we have a graph that is this, right? This equation is obviously not, I mean, this is not exactly what the graph looks like, but I just want to give a visual here. Imagine a graph that has an S-shaped or anything that has that doesn't pass a vertical line test, right? And if you only have the x value, then this derivative is going to kind of be confused. It's not going to know, okay, you want me to find the slope of at x equals 2 at this point, or this x equals 2, or this x equals 2, right? Because there's all these x equals 2s, but it needs the y value as well. So if you give it the y value, then the derivative is going to know, oh, okay, all right, you want me to find the derivative of this point. Okay, that is, slope -2. Or if it's this point, then it's slope of 2. If it's this point, it's slope of -1/2, right? So that's why the derivative looks a little bit different. It needs more information because of the fact that your equation, is going to have some conflicting or duplicate x values that may show up on the graph. Okay, so that's why it needs both the x and y values sometimes. Okay, any questions so far? All right, let's go to page 32. Okay, 3xy cubed minus 2y equals 7. We want to find the derivative. We can do dy dx, it says find dy dx of y prime. We could replace every derivative with y prime instead of dy dx, but I prefer dy dx because it's more descriptive, and if we do y prime, sometimes it can be misread as a y to the first power, and it just feels it's more work to write this down, but I think it's nice to just keep that variable. Now, if you did y prime on a test instead of dy dx, it won't be wrong. I won't take any points off, but I'm going to present it using dy dx. Okay, first, do we see the need for implicit differentiation? Yes, right. You see y's that feels out of place, or multiple terms, or something. We'll see that y cubed, right? Something feels a little bit off about that y. It's not isolated from the x variable. Okay, so we know there's implicit going on. There's another process that's involved here. It's kind of tough to see. Can you identify what other process is involved besides just power rule and implicit? It has to do with this 3xy cubed. Anything stand out about that?
Maybe.
It'd be multiplied. So I got to do product rule. And that feels a little bit difficult to see because you're looking at that going, well, that looks like one term to me. Why do I need product rule? Because we have two different variables and they're being multiplied with each other. Now, if it was 3x times x cubed, I'll be able to merge them together and just do power rule. But here, 3x and y cubed are different variables. They cannot be merged to the same variable. And they're being multiplied. So that's going to have to that's going to have to require us to go through a product rule. So put a star next to this because, with implicit differentiation, I don't think it's too difficult to understand, but it is easy to miss product rule because the problem is not going to announce itself and say, hey, do product rule here. Or maybe it'd be helpful if there's actually parentheses like 3x y cubed, but that's not how the problem will be presented. So we need to be able to, kind of train ourselves to understand, oh, that's product rule, and I need to apply product rule because I see two variables connected by multiplication. So let's set up using product rule, and then we'll finish off the rest. Okay, so f prime g plus f g prime. What's f prime? 3x becomes 3. What's g function? Q. Back to f. 3x. All right, what's g prime? 3y squared. Is that it? dy dx, right? So every time we involve y's derivative, we need to include that dependent variable derivative. Oh, sorry, not equals, minus. So all that is to take care of that 3xy cubed. So now we're done with that portion. Let's keep going though, right? We haven't finished off the rest of the derivatives yet. Okay, minus 2y becomes minus 2. Anything else? dy dx, right? Even though the y disappears, we are asking for y's derivative, and then equals 0. Okay. Calculus is done. Now it's just a matter of rearranging and trying to get dy dx by itself. Okay, so how many dy dx terms do you see? 2. So we're going to leave these 2 on the left. We'll move this where? To the right side, yeah. And then once this is by itself, we can factor out a what? dy dx. We're going to see a set of parentheses, and then just move to parentheses. And what else can I do here? Or them together, right? Okay, so try that. See if you're able to work your way through, and it's just algebraically trying to eventually get dy dx isolated on the left side and everything else on the right side. Any questions algebraic wise here? Okay, example 3 is not going to be on the test, but it's just a bit of a preview into the next section. And it's the fact that if we have a different variable that's independent, then that is going to have to play a role in our derivative. So everything up to this point, what's been the independent variable? It's been x, right? So that's why everything has been over dx, or dx in the denominator. But here, if t is the independent variable, that means everything is going to be impacted by time, or time t. So now t is the independent variable. And what that means is that we're still going to go through the same process. We're still going to find the derivative. We're still going to attach a differential variable. But now it's going to have to take a certain form. It's not going to be a d, whatever that variable is, divided by d. No longer dx. It's now going to be over dy dt. Yeah. So we don't exactly know what that means yet. We'll talk about what that means once we do 2.6. So after we get done with this unit, we have something called related rates coming up, and that's 2.6, and we're just going to have a unit just for that section. It's big enough that allows us to just focus on that one topic for an entire unit. So let's just go through this process. Just understand that, oh, time is not my independent variable, and now everything is going to get impacted by this d over dt. So let's find the derivative here. Y squared becomes what? 2y. We want to find the derivative of this variable, so we do what? D. Okay, but what do I fill this blank with? dy, yeah. dy over dt, because this problem has announced itself to be time being t being the independent variable, equals, okay, what does 5x become? 5, but x is no longer the independent variable. We need to attach a what? Dx, yep, dx over there. So that's the derivative form in terms of what we solve for. We'll talk about that later in terms of the next unit, but I just want us to introduce, if there's a different variable, different independent variable, that's going to show up in the denominator and, instead of x. Okay, so I just want us to focus on implicit differentiation with x being the independent variable. This is just a preview. So any questions so far? All right, if you guys can turn to page 33. And we're going to step through 2, 5, and 7. Okay, do we see the need for implicit for number 2? Yes, okay. You're going to find the derivative. You're going to have dy over dx show up, right? Dy over dx for the y's, right? Okay, so just wanted to point that out. Now, before you guys start, let me just kind of run through the things that I want you to pick up on for these problems. Okay, so I'll give you guys a chance to start to number 2. Number 2 is easy, but number 5, look at number 5 for a moment. Does anything stand out? Well, first off, do you see implicit built into this problem? Yes, right. If you see y's everywhere or something done to the y variable, it's always implicit. Okay. Anything else stand out about this problem? Product rule. Okay. Good. All right. There's something else. Very, very subtle. No, everything is the product rule, power rule. 7 goes to 0. But there's something else that we got to be careful about. Yeah. What about this minus is troublesome? What's going to happen after product rule? Yep. There's that plus sign that shows up, and if we're not careful, that negative, we're going to forget to distribute, and that's going to throw us off. So my solution to that is you do product rule the way you normally would, but then just protect your product rule with a set of parentheses, and that way, when you're ready to clean up, you're going to be reminded, oh wait, I need to distribute a negative through, and that's going to help you remember. So as you do product rule, just do f prime g plus f g prime, but keep your result in a set of parentheses so that you can remember that the negative has to have an impact with that expression. Okay, and then number 7. What's going on here? Implicit and product rule. But this one is a little bit cleaner. Okay, but there's something about that y I do want to point out, but we'll get to that. But go ahead and try number 2 and 5 first. Okay. I'll come back and I'll step through each problem with you. Okay. x squared becomes 2x. Y squared becomes 2y. Don't forget, dy dx is going to impact every derivative for y variable. Don't forget, 25 doesn't stay 25, it goes to 0. And that's it. That's the only calculus step involved here. The rest, you're just trying to add, subtract, multiply, divide, whatever it takes to get that dy dx by itself. Subtract the 2x over first, divide both sides by negative 2y, reduce, and then you're down to your derivative equation, your slope formula. Okay, any questions with 2? All right, so number 5, we know that we got to go through product rule for that middle section. We're going to protect that with a set of parentheses. So when we do f prime g plus fg prime, we're still leaving that set of parentheses there. So after the derivative, we'll remember to distribute. Okay, let me go through it step by step here. X cubed becomes 3x squared minus, I'm going to create a big set of parentheses for my product rule to live in. Okay, f prime. 1, good. G function, no changes. F, no changes. What does G prime become? 1 dy dx, yeah. Okay, we're not done yet because that will take care of that middle portion. We'll distribute the negative later, but let's finish off the rest of the equation. Okay, y squared becomes, is that it? Dy dx, yeah. We're asking for y's derivative. We need to include that dy dx. Okay, equals 0. Before we go on, let me just point out something that I see some students make here. Why do we not include dy dx here? I mean, there's y here, so why not a dy dx here? Good. It's not asking for the derivative, right? It's just the original g function. We're only going to involve dy dx first if it's derivative being asked, and if there's a variable y to deal with, right? Those two things have to come in play if we want a dy dx to show up. Okay. All right, so now the calculus is done. We're just going to clean this up here, distribute the negative through. Identify the terms that have dy dx so that we can know which ones to keep on the left side and which ones to move. We want to keep the dy dx terms on the same side, and the non-dy dx terms we're going to subtract or add to the other side. And then once the dy dx terms are isolated on the same side, we can then factor that dy dx out. Finally, divide that parentheses over. Okay, so we should get y minus 3x squared divided by negative x plus 2y. Any questions there? Okay, number 7. Do we see the need for implicit? Yeah. Do we see product rule? Yes. Okay. But there's no negative in front, so we don't have to worry about changing the signs. But there's something that I want to point out about that second term. We'll get to that. Okay, so we'll do product rule first. Okay, f is the x cubed, g is the y cubed. Okay, so f prime becomes squared times y cubed. No dy dx, right? We're done asking for the derivative. Okay, plus x cubed times 3y squared. Anything else? Yeah, we need to attach that dy dx. Minus, what does y become? 1 and then dy dx. Now, my suggestion is, technically you don't need that 1 there, but I think that 1 is going to come in really handy when you're factoring. So I think for the sake of us not making a mistake further on, that 1 is going to be extremely helpful. Now, if you don't put a 1 there, you're not losing points, but it could impact the way you clean up the process. So it's nice to have that placeholder. I'll talk about what that means in a second. Put a 1 there, and I'll show you how that's going to help us out down with the next step. Okay, equals. Good, right? So don't forget, I think the tendency is when we see something by itself, we feel like it's not getting impacted, but it is. So everything is getting impacted by the derivative, so it becomes 1. Okay, so next step, we want to get the dy dx terms together. So I see 2 of them. So those 2 will be on the left side, everything else on the right side. Just gonna clean it up a little bit. You don't have to, but I just like my coefficient in front. Okay, I got to factor out dy dx. What's left? Oh, sorry, my bad. Let's stop you then. Sorry, this one, it is x cubed y squared. I just put that here and I move this over here. Sorry, x cubed y squared. Okay, is there anything else inside the parentheses? -1, okay. Now, it's easy to make that jump, right? See that -1 there? But imagine if you did not put a -1 there. If you just did dy dx, it's not wrong, but I think if you don't see that -1 there, what do you think some students could end up doing?
Just not putting
Just
anything.
not put anything there and say, well, I took everything out, so I was going to have dy dx 3x cubed y squared. But having that 1 there is a reminder, oh, I took a dy dx out, I still have something there. It's not, doesn't completely disappear. There's still a 1 there. So having that is very helpful, I think. Equals. All right, so almost there, right? Divide by the parentheses and we're at our derivative. Okay, there's our slope formula. Can I do this? Can I start canceling stuff out? No. Right, and I see some students do that and they start taking everything away and they end up with 0 for the derivative, right? So start taking the 1 out, start taking the 3 out, start taking the x out, the y out. We can't do that. As soon as if there's a minus or plus separating terms, it's stuck. We can't, we don't have an easy time, and it's okay to leave your answer unsimplified. Okay, last problem, next page. We're going to do a tangent line equation, which you know the drill there. You're going to find the derivative, and then you're going to insert the x value and the y value into the derivative to get your slope. And then finally, you just do point slope form. So let's go down to the bottom of the page, there are 51. And let's just go through the process. You have the ordered pair, so that's given to you. We just have to find the derivative, find the slope, and then point slope form. So these are just nice, clean power. Well, first off, do we see a need for implicit? Yes, right. There's something done to the y. I know y is by itself, but you see that square root, right? If there's any operation done to the y, we have to go through implicit. But first, I would just rewrite it. Get that radical to be rewritten as a rational exponent. And then it should be nice, clean power rule, right? X to the 1/2 becomes what? 1/2 x to the negative 1/2. Okay, so straightforward. How about y to the 1/2? Good, times dy dx, right? We got to do dy dx for this variable. And then the 5 goes to a 0. Okay. All right, so now it's just a matter of cleaning up. I like to just resolve the negative exponents. Makes it easier for me to think about them. So I'm just going to move that x and y down to the denominator, share the same space as the 2. And just visually, I just find it a little bit cleaner to look at square roots instead of the 1/2, but either form is fine. So we'll subtract the subtract the 2 over root x, 2 root x. Sorry, the 1 divided by 2 root x to the other side. Okay. What's next? Divide by the fraction, right? That's kind of ugly. So dividing by a fraction, though, is same thing as multiplying by the reciprocal. So that feels a little bit cleaner. So I'll do negative 1 over 2 root x times 2 root y over 1. So dividing by a fraction is the same thing as multiplying by the reciprocal. Go ahead and multiply through. Get the 2's to cancel out. I'm left with negative root y over root x. That's my slope formula. So then how can I find my slope? Plug in my x and y. Yeah, so my slope formula now requires many times more than just one variable. So I need both variables. Sorry, both order pairs inserted in. Now this notation feels a little bit different because if I want to find the derivative with 2 order pairs, I'm going to use this notation, this vertical bar with parentheses to indicate it's not just f prime of 9, right? It's f prime of 9 comma 4. And then with this dy dx notation, we use this 9, 4 to indicate, oh, I'm going to insert both numbers into the derivative to get my slope. And then once you have your slope, you take your order pair and then point slope form. Okay, you guys have homework tonight over implicit differentiation. Check with the keys on the website and try your best through them, and then we'll start our test review tomorrow. Okay, come up and get your phone.